Let's continue from the previous exercise, but let's spice things up a little bit. Rather than having a linear map, we add this mod 1 here so that we have a nonlinear map. Now the question is, can you show that the point 1/3, 1/3 is a periodic point of this nonlinear map with period 4? So this is a bit more complicated. Pause the video and see if you can figure out how to tackle this problem. So a quick reminder of what this mod 1 stuff actually means. So if you have, for example, 1.1 mod 1, it just means that it's the remainder after division by 1. In this case, this will give us 0.1. So it's basically the stuff to the right of the decimal point that this mod 1 operator means. Now we started from a linear map A, which is 2, 1, 1, 1. And then we turn this into the nonlinear map A mod 1. Okay. But now we're looking for fixed points of order k, so period k points with k equal to 4. So now we're looking at that same map, the map A mod 1, but we apply that map 4 times. And then we need to figure out if 1/3, 1/3 is a fixed point of that new map. Now what we can do is look at this for a while and then realize that we don't need to have this mod 1 operation for all of the intermediate steps. It's actually just sufficient to do this mod 1 operator at the very end. So just calculate a to the 4th and then only do the mod 1 at the end, in the final calculation. Now, in order to convince yourself that that's indeed the case, first of all, let's think about what this multiplication by this matrix actually means. The only thing it does to x and y is multiplying it with these constant factors here, and then also taking the sums, so just linear combinations. So let's have a look at linear combinations and whether or not we need all the intermediate mod operations or whether we can just get away with using a mod operation at the very end. So let's give some examples of two numbers, first of all for summation. So let's say we have 1.1, and then we need to do mod 1 plus, let's say 1.3 mod 1, and then finally we have mod 1 at the end. So again, this is just a hypothetical calculation here, has nothing to do with this particular matrix. It's just to illustrate that for summation and later on for multiplication by constants, we don't really need these intermediate mod operations. As you can easily see, because this basically gives us, so 1.1 mod 1 is 0.1. Here we have 0.2. If we calculate that, mod 1, we have 0.3 mod 1. So this is going to be 0.3. Now, if we calculate that without the intermediate mod 1s, so we just do 1.1 plus 1.2 mod 1, this gives us 2.3 mod 1, and that's also 0.3. So at least for summations here, this means that you don't really need these intermediate mod operations. And you can do something very similar for multiplication by a constant. Let's again give an example. Let's use, for example, 2 times 1.1 mod 1 mod 1. So this is going to give us 2 times 0.1 mod 1 or 0.2 mod 1, that's 0.2. And this is indeed the same as when we get rid of the intermediate mod 1, because that gives us 2 times 0.1. This gives us 2.2 mod 1, and that's also 0.2. Okay, this is just perhaps too much explanation to show the important part is that we can move this mod 1 operation just to the very end. So now the next step is figuring out if our point 1/3, 1/3 is indeed a fixed point of this particular map. So pause the video and start the calculation. So for that calculation, we first need to calculate a to the power of 4. That's not difficult, it's just slightly tedious. So let's see what happens. So a is 2111. That means that a squared is 2111 times 2111. So this gives us 2 times 2 is 4 plus 1 is 5. And then 2 plus 1, so that's 3. And then also here we have 3. And 1 plus 1 is 2. So we have 5, 1 plus 1 is indeed 2, as I said. So we have 5, 3, 3, 2. That's a squared. Okay, let's say we're halfway there. Now for a to the power 3, we have 5, 3, 3, 2. And then times 2, 1, 1, 1. Okay, 2 times 5 is 10 plus 3, so that's 13. And then 5 and 3 is 8, also an 8 there. And then finally for the lower right, we have 5. So a to the power of 3 is 13,885. And then finally, thank God, we have a to the power 4 is 13,885 times 2111. Okay, let's get going here. So 2 times 13, 26 plus 8, 34. And then 13 plus 8, so that's 21. Also 21 there, and then 8 plus 5 is 13. So the map a to the power 4 is 13, 21, 21. Sorry, 34, 21, 21, 13. Okay, so luckily that's finished. What we now need to do is figuring out if we're dealing with a fixed point of that map. So we need to calculate a to the power of 4 of 1/3, 1/3 mod 1. And if this brings us back to 1/3, 1/3, then we indeed have a fixed point of this map, or a period 4 point of our original map. So if we factor out this 1/3 here, then we have a to the power of 4. That's going to be 34, 21, 21, 13. And then 1, 1, and then mod 1. Okay, so this is going to give us 1/3. And then we have 34 plus 21. So this is going to give us 55. And then 21 plus 13, that's going to give us 34 mod 1. Now let's see what happens to these guys after dividing by 3. What's the remainder? Now 55 divided by 3, that doesn't work in the integer field. But if you look at one less, if you look at 54, that is divisible by 3. So the end result here is, after taking the modulo 1 operator, that we have 1/3. And then finally for this 34 over 3, well, if we do one less, 33 is divisible by 3. So for the remainder, we also have 1/3. And indeed, we get back our starting points 1/3, 1/3, which shows that this is indeed a period 4 points of our original map.